Okay, so we are about to go on an incredible journey. We're going to see how a simple rock, literally dug out of the earth, gets transformed into one of the most powerful and concentrated energy sources on the entire planet. This is the story of nuclear fuel.
It seems like a simple question, right? But the answer? Well, it involves one of the most complex industrial processes you can imagine. It's this amazing journey of chemical and physical change, all designed to unlock an absolutely incredible amount of power. And to get to that power, our story has to start right here, deep in the ground. Uranium ore is dug up from these massive pits. This is the very first step, taking huge amounts of earth just to start concentrating a naturally occurring element. And here is the end goal of that entire massive mining operation. This one tiny ceramic pellet. I mean, the contrast in scale is just staggering, because this little thing holds a truly incredible amount of potential energy.
So the big question is, how in the world do we get from that giant pit in the ground to this potent little pellet? Well, let's dive into the first stage and see how that raw rock gets its first major makeover.
This map kind of lays out the whole journey for us. We're starting right up here, in the top left, with mining and milling. The goal at this stage is pretty simple, actually. Take enormous quantities of rock that have just a tiny bit of uranium in them and refine it all down into something much, much purer. It's basically a three-step recipe to get the good stuff out. First, you just crush all that rock into a fine powder. Then, you use acid to leach out the uranium, basically dissolving it so it separates from the waste rock. And finally, a chemical process called solvent extraction isolates and purifies that uranium. And after all that crushing and dissolving and purifying, this is what you get: a concentrated uranium oxide powder. And, thanks to its color, it gets a very fitting nickname: yellow cake. But here's the thing. Yellow cake isn't quite ready for a reactor. To generate power really efficiently, the uranium needs to be enriched. Now, that just means increasing the concentration of a specific type of uranium atom. And to do that, we first have to turn it into a gas. And this is where it gets really interesting. To enrich uranium, you have to turn it into a gas. Specifically, this stuff, uranium hexafluoride, or UF6. It has this really unique property of turning from a solid to a gas at a pretty low temperature, which, it turns out, makes it perfect for the whole enrichment process. Okay, I know this looks complicated, because it is. It's like a chemical gauntlet designed to purify the yellow cake and completely change its molecular form. It takes it from a solid oxide through all these different solutions and reactions, all to get it ready for that final conversion into a gas. So what this all really boils down to is a three-stage conversion. The yellow cake is refined into a pure brown powder. That powder is then reacted to create a green solid. And finally, that solid is exposed to fluorine gas, and poof, it transforms into the uranium hexafluoride gas we need for enrichment. All right, so after the enrichment process is done and we have a higher concentration of the useful U-235 isotope, the journey does a complete 180. After all that work to make it a gas, we now have to turn that valuable gas back into a very specific and very tough solid. So first, that enriched gas gets converted back into a stable powder, uranium dioxide. This fine black powder is now enriched, and it's going to be the raw material for the fuel pellets themselves. Next up, that powder gets squeezed, and I mean squeezed, under immense pressure. It's pressed and compacted into these dense little cylindrical pellets, each one perfectly formed for the next part of its transformation. But they're not done yet. They are then baked, or sintered, at incredibly high temperatures. This process turns them from just a compacted powder into a really tough, heat-resistant ceramic. And that is absolutely essential for surviving the intense environment inside a nuclear reactor. The scale here is just wild to think about. These tiny ceramic pellets, right? Each one is no bigger than a pencil eraser, and they are carefully loaded one by one into these long, slender metal tubes made of a special alloy that won't corrode. These individual rods are then grouped together into a precise grid, which is called a fuel assembly. You can think of it as the final, complete package that's all ready to be lowered into the core of a nuclear reactor and start making some serious power. But what happens after that fuel has spent years generating immense amounts of heat and electricity? Well, its journey still isn't over. Let's take a look at the final chapter, what we do when it's considered spent.
Now, when fuel becomes spent, it's not because it's out of uranium. It's because the concentration of those special energy-releasing U-235 atoms has dropped too low to keep the chain reaction going efficiently. And what's really important to understand is that this spent material is still incredibly energetic. It's got leftover uranium, newly created plutonium, and a bunch of other byproducts from the reaction. This whole mix is what makes it highly radioactive, and it's the main source of what we call nuclear waste. And it's also really important to know that not all nuclear waste is created equal. It's all carefully classified by its level of radioactivity. Everything from slightly contaminated stuff like tools and clothing all the way up to the intensely radioactive spent fuel itself. And what might surprise you is just how little of the total waste is actually the most dangerous stuff. This high-level waste, it only makes up about 3% of the total volume. But, and this is the real kicker, that tiny 3% of volume contains a staggering 95% of the total radioactivity. It is an incredible concentration of energy that has to be managed with extreme, extreme care.
So, this incredibly complex journey from rock to rod, it solves one huge challenge: how to create vast amounts of clean energy. But it leaves us with another critical, long-term question to answer. What is the final destination for its incredibly potent legacy?